session, right. So, in the last session we had seen the one example of root locus, right. So, now in today's session we will discuss the another examples of root locus, which we will discuss in detail. So, today we would like to understand the concept of angle of arrival and departure, and we would like to see what will happen if we add a pole or 0 in the system, then how it is going to affect the root locus. So, to understand it, we would like to go for this transfer function. Okay. So, here a negative feedback or unity negative feedback system is given, where it means H s is equal to 0, sorry, H s is equal to 1, and this is our transfer function G s equal to k over s plus 2 s plus 4. So, we are adding this extra pole in our transfer function. So, in the last lecture we discussed the root locus of k over s plus 4. Now, today we are adding one pole at location of -2, and we would like to see what would be its impact on the root locus. Okay. So, here I would like to see my number of open loop poles. So, number of open loop poles are here s equal to 0, -2 and -4. Okay. Now, I would like to calculate number of poles terminating at infinity, it is n equal to p minus z. So, here number of poles are here 3, number of zeros are 0. So, 3 minus 0 would be 3. So, n value is 3, it means number of pole terminating at infinity is here 3. In the same way, we would like to calculate here my angle of asymptote, it means in which direction these pole will terminate to the infinity. So, I will write here 2q plus 1 multiplied by 180 over p minus z. Okay. So, this is the case. Now, whenever my n is 3, so I told you in the last lecture, so q value would be 0, 1 and 2. Okay. So, now you can put here, when you put here q value is equal to 0, you will get 1 angle 60. When you put q equal to 1 here, you will get one next angle would be 180. Okay. When you put here q equal to 2, you will get here next angle would be 300. Okay. So, this would be the basic angles that you will find whenever my n equal to 3. So, whenever you calculate phi for n equal to 3, you will always get these 3 angles. Now, we would like to know what would be our valid reason on the root locus. So, I can draw this pole on our j omega axis. Okay. So, here one pole is lying at the origin, one at -2, one at -4, right. And if I look the value of k, my value of k is equal to 0, my value of k is here equal to 0, my value of k is here 0. Now, I would like to know for what is my valid reason of the root locus. So, if I am standing here, number of pole is 1, it means this reason is valid reason. If I am stand here, I will find 2 poles in my right side, it means count is even, this will not be a valid reason. If I am standing here, number of pole count is 3, it is odd number, it means this reason till value of minus infinity is the valid reason of the root locus. Okay. Next step is we need to calculate our centroid. Okay. So, here our centroid point is given as summation of p minus summation of z over p minus z. So, number of poles summation of p is how much, you can see from the above equation is 0, -2, -4, p minus z is here 3. So, this will gives you around -2. So, centroid point is here -2. Okay. So, from -2 point we need to draw 3 angle, it means one pole at origin, one at -2, one at -4. So, from point -2 I will draw 3 angle, one is going for 60, one is going for 180 and one is going for 300. Okay. So, this will be your 60, 300 and 180. So, these 3 lines are telling us how our pole is approaching to the infinity, right. So, our next step is we need to calculate our breakaway point. Okay. So, for breakaway point we need to put 1 plus GSHS equal to 0. It means 1 plus k over you can say s multiplied by s plus 2 multiplied by s plus 4 equal to 0. You have to solve it. This will gives you s square plus 6 s, you can say s square plus 2 s plus 2 s, and if you further solve it, s square plus 2 s multiplied by, you can say, s plus 4 is here, and further if you multiply it, you will get s square s cube plus 4 s square plus 2 s square plus 8 s. Okay. So, if you solve it, so you will get here in the numerator s cube plus 6 s square plus 8 s plus k is equal to 0. Now, you have to equate k in terms of s minus of s cube plus 6 s square plus 8 s. Okay. Now, you need to calculate dk by ds. Now, put equal to 0. When you equate to the 0, then you will get first differentiated 2 s square plus 12 s plus 8 equal to 0. If you solve it, so you will get here two value of s, that is one is around minus 0.84, second is around minus 3. So, you if we see minus 0.84 lying where, so minus 0.84 lying here in the valid region, and if we look for our next value is here minus 3. So, where is minus 3? You can see minus 3 is lying here in the invalid region. So, we can say minus 0.84 is our valid region of root locus. Okay. So, in this case I will assume minus 0.84 is our valid root locus, and we will discard the value of minus 3. Now, we would like to see what would be our root locus. Okay. So, now draw the complete root locus, one pole at origin, one pole at minus 2, one pole at minus 4. We had seen our breakaway point is 0.84 near around. Okay. So, what will happen, one pole is available at origin, it will try to move towards the breakaway point, it will come here. This pole at minus 2, it will move towards the breakaway point and it will meet here. Now, in which direction they will move towards the infinity, then they will look for angle of asymptote. So, you have seen in the previous graph that angle of asymptote going here in the direction of 60 degree, it means this would be my angle of asymptote. One is this direction of 180, one direction of 300. It means one pole will rise above, you can say it will go like this, and then the direction of it will move here, right. In the same way, pole at minus 2, it will come to breakaway point, it will go down, and then in the direction of this asymptote, it will try to approach towards the infinity, right. This is happening, and the pole at minus 4, it will follow the angle of asymptote of 180 and it will moves to the minus infinity, right. So, this is the root locus corresponding to this, right. So, this is the valid region between 0 and minus 2 and minus 4 and minus infinity, and this is the invalid region of the root locus. Now, you can see by addition of pole, my root locus is coming towards the imaginary axis. Okay. So, now you can see if my root locus lying in the right half plane, it means this is the situation of instability. Whenever my root locus touching the imaginary axis, you can say this point and this point, you can say this point is condition of marginally stable. Okay. So, we can say this system is stable for fixed value of k, not every value of k. Okay. So, for which range of k this system is stable, we have to calculate it, and with the help of root locus we need to determine what is the stable range of k. Okay. So, for that purpose we need to see the equation 1 plus GSHS Okay. So, you can see this was our equation. Okay. So, from here you can calculate the range of k. So, here is s cube plus 6 s square plus 8 s plus k. This is our 1 plus GSHS equation, quadratic equation. Now, I need to draw Raoult-Harvey's for it, s cube, s square, s 0, 1, 8, 6 and k. Now, try to solve it. 48 minus k over 6 and then k. So, for stability my first column should be positive, it means k should be greater than 0, and 48 minus k over 6 it should be greater than 0, and you will get a condition k less than should be 48, right. It means at imaginary axis my value of k is here 48, and my initial value whenever I look for the open loop pole at origin, k value is 0. When I keep increasing the value of k from 0, it will move towards the breakaway point, and if I keep increasing k till 48, then you can say if my k is less than 48, then my system is stable. At k equal to 48, my system would be marginally stable. At k greater than 48, my system would be unstable. Okay. So, now we would like to know at which point this root locus intersecting the imaginary axis. Okay. So, we can say intersection point on the imaginary axis. So, intersection point on imaginary axis. So, how it can be calculated? We can calculate with the help of this auxiliary equation. So, we have to write this equation as 6 s square plus k equal to 0, where k we determine for marginally stable condition k equal to 48. So, 6 s square plus 48 equal to 0, or you can say s square is equal to minus 8, or s equal to, you can say it is under root of 8 j, or it is around 2 root 2, around you can say plus minus 2.8 j. You can solve it, you can get the exact value of s. It means this value is plus 2.8 j in the positive axis, and this point is minus 2.8 j in the negative axis. So, in this way we can calculate the point of intersection of root locus on the imaginary axis. So, here Raoult table help us to calculate the range of k for stability, and you can say from auxiliary equation we can determine the point of intersection. Now, you can see by addition of pole our system is what? It is shifting towards the imaginary axis, and our relative stability decreases. So, we can say our relative stability decreases by addition of pole. Okay. Now, we will see our next example where we are adding 0 in the transfer function, same transfer function we are taking, and here it is G s equal to k multiplied by s plus 1 over s plus 2 s plus 4, right. So, now we need to calculate the open loop poles, same it is 0, minus 2, minus 4. Now, open loop zeros, it is here at minus 1. Now, one 0 is coming in the picture. Now, we would like to see what would be the root locus. Now, second step we need to calculate n equal to p minus z, number of pole is 3, open loop pole is 0, 3 minus 1 is equal to 2. So, whenever my n is equal to 2, it means 2 pole is going to terminate at infinity, 1 and you can say third pole will terminate at the 0. How it will? We will see with the help of root locus. So, now we would like to know what would be my angle of asymptote. So, it would be given by 2q plus 1 over 180 divided by p minus z. So, here it is what would be value of q when n is 2, q would be 0 and 1. If you solve it, you will get 90 and 270. Okay. This is our angle of asymptote. Now, we need to calculate here the valid region on the root locus. So, we will draw in the next page. Before that, we can calculate the centroid point, summation of p minus summation of z divided by p minus z. So, number of pole you can say it is 0, minus 2, minus 4, this is summation of p, minus of 0, 0 is here at s equal to minus 1 divide by p minus z is equal to 2. So, this will gives you minus 5 by 2, and if you solve it, it is minus 2.5. So, from minus 2.5 we will draw the angle of 90 and 270. Okay. So, we will see in our next step. We have to draw first valid reason on the root locus, one pole at origin, one pole at minus 2, one pole at minus 4, and one open loop 0 at minus 1, right. So, now what is the valid reason of root locus? If I am standing here, this is the valid reason. If I am standing here, even number, not valid reason. If I am standing here, count is 3, 2 pole 1 0, valid reason. If I am standing here, 3 pole 1 0, count is 4, invalid reason, right. So, this dashed line is the valid reason of the root locus. Okay. Now, my centroid point is coming at 2.5, you can say at this point. So, if I draw one angle is going toward 90, second angle is going towards the 180, okay. Sorry, 270, not 180. So, this is the angle which will tell us our pole going to the infinity. Now, what is the point? That is the breakaway point where this pole will leave the real axis. So, we need to calculate here breakaway point 1 plus GSHS equal to 0. We will write here 1 plus k multiplied by s plus 1 divided by s multiplied by s plus 2 multiplied by s plus 4 equal to 0. If you solve it, you will get here you can say s multiplied by s plus 2 multiplied by s plus 4 plus k multiplied by s plus 1 equal to 0. If you shift in terms of k, s plus 1 equal to minus of s multiplied by s plus 2 s plus 4. If you further solve it, the value of k would be equal to divide by s plus 1, and then you need to calculate dk by ds equal to 0. If you do this calculation, then you will find the valid breakaway point s equal to around a minus 2.9. Okay. So, you can solve this equation and you will get the multiple value. The valid value would be here minus 2.9. It means this would be my breakaway point. So, what would be my root locus? Okay. So, here I can draw here basically in this slide, and it would be good. From the reference we can draw. This is my pole at origin and 1 0 at 1, then pole at minus 2, then pole at minus 4. This is the valid reason and this is the valid reason. My breakaway point near minus 2.9. So, what is happening? The pole at minus 2, it will move towards the breakaway point, and then it will look for angle. My angle is 90 degree. So, it will move in the direction of you can say 90 degree and reaches to the infinity. This is the movement of my pole at minus 2. Now, with the pole sitting at minus 4, it will move toward the breakaway point, overlap at this point and move towards infinity at angle of 270. What about third pole? This pole will move towards minus 1 at 0, it will terminate. So, if you see, the value of k is here 0, value of k is here infinity, and value of k is here 0. The value of k is 0. Where k is 0, this is the starting point, where k is infinity, this is the terminating point. So, now by addition of 0, you can see our root locus shifted away from the imaginary axis, and for every value of k, this system is stable. Okay. It means, if we add 0, our system will become stable in nature. Okay. The same way, one more question we can see. So, here a root locus is given and we need to say what is the range of k for which our system is overdamped. So, this is the root locus, various value of k is given, right. So, we can say for overdamp, what is the condition? Our root should be real and distinct. Okay. So, if you observe here, the breakaway point is here at k equal to 1 and break in point is here at k equal to 5. So, what is happening here? Overlapping of pole. Or it is happening at real value. So, this is the critical case or critical system or critically damped system. Okay. So, whenever my k is greater than, you can say 1, it is going in imaginary axis. It means it is under damped, it is complex, and whenever my k, you can say less than 5, because at k equal to 5 again it is returning back to 0. It means whenever my k less than 5, it will remain complex. So, this will be the condition of under damped, and when my k, you can say, is less than 1, you can say this region, but greater than 0. So, this would be over damped, because in this region I am getting real and distinct root, and whenever my k is greater than 5, then I am getting real and distinct root. It means this would be the case for over damped. So, here you can see option D is correct if k is greater than 0 and less than 1, or you can say if k is greater than 5, it will become under category of over damped. Now, we would like to see the concept of angle of departure. So, this is the angle which will tell us if complex pole present in our system, how they will depart to the infinity. So, for that purpose we need to calculate the angle of departure is given by 180 plus phi, and this phi is given as summation of phi z minus summation of phi p, where phi z is the angle contribution by 0, phi p is the summation of all the angle contribution by the pole, right. In the same way, angle of arrival, suppose complex zeros are here, in that case what will happen? This formula phi a would be given by 180 minus phi, this symbol will change, here it is plus, here it will be minus, and phi will remain same, phi is the summation of phi z minus summation of phi p. So, to understand this concept, we need to solve this numerical. Here again GS is given, we need to draw root locus for it. So, here we need to calculate the open loop poles. So, it is coming at s equal to 0 minus 6. If you solve it, so you will get minus 2 plus minus 3 j, right. So, these are the poles. If you plot here, one at the origin, one at minus 6, one at you can say minus 2 plus 3 j. Suppose this is minus 2 and this value is here plus 3 j. In the same way, this value is here minus 3 j. So, this is the location of pole, right. So, now we need to calculate here the angle of departure. So, before that we would like to calculate the valid region on the root locus. Okay. So, how we can calculate the valid region on the root locus, we will see. So, first we need to calculate here number of pole going to terminate at infinity, n equal to p minus z. You can say number of pole is here how much? 4, zeros are 0. So, n is equal to 4. Now, we need to calculate phi angle of asymptote 2q plus 1 multiplied by 180 divided by p minus z. Okay. So, here what would be value of q? Value of q would be 0, 1, 2, 3, because n is here equal to 4. So, in that case we can say phi value would be 45, and you can say next would be 135, next would be 225, and next one would be here 315. Okay. So, this would be the 4 angle for different value of q. Okay. So, now this is the angle of departure. Now, we need to calculate the centroid point C, summation of p minus summation of z over p minus z. So, summation of p, you can say it is here 0 minus 6, right. So, now this summation of p will tells only the real value of pole if complex pole is present. So, I will take here only minus 2. So, this and second is here minus 2. Okay. So, two poles are here, it is complex pole, divide by p minus z, p minus z is 4. So, this is around you can say minus 10 by 4 and it is around minus 5 by 2, around a 2.5. So, this would be my value of centroid. Okay. Now, I can draw this 4 angle from the value point of centroid. So, before that we would like to know what would be the angle of departure. So, here if I draw from minus 2.5, one angle is for 45, one angle is for 135, then 225, then 315. Okay. So, now we would like to see how this complex pole will departure. So, we need to calculate this phi angle of departure. So, I have to assume this is my pole. Now, I will calculate its angle from this pole, its angle from this pole and angle from this pole. If 0 is present, you need to calculate the angle contribution from 0 also. So, this angle is phi p 1, this angle is you can say this angle is phi p 2 and this angle is phi p 3. So, what is this angle phi p 1? You have to calculate from the anticlockwise. So, this would be equal to 180 degree minus tan inverse of the distance along the x axis is here 2, right, and imaginary axis is 3, tan inverse of 3 by 2. So, if you calculate, it is around the 123.6. Phi p 2 it is making angle of 90 and phi p 3 this is making the angle of tan inverse of 3 and this distance is 4. So, phi p 3 would be tan inverse of 3 by 4, it will come around 36. So, what would be the phi? Because for angle of departure we know that it is 180 plus phi and phi is given as summation of all the angle from pole minus summation of all the angle from 0. So, here phi p summation of phi p would be given as phi p 1 plus phi p 2 plus phi p 3, this is 0. So, here it can be you can say 123.6 plus 90 and phi 3 is around 36. If you calculate, it come around 250 approximate value, not exactly. Now, my phi d it is minus 250, phi d would be around 180 plus phi around minus 70. It means my angle of departure is here phi d is equal to minus 70. It means this pole will depart at angle of minus 70 and approach to the infinity, and the pole at the bottom for this phi d would be plus 70 because it is symmetric. So, now see the root locus, final root locus for it. One pole is here, one pole is here. Okay. So, you need to calculate the breakaway point for this, it come around minus 4. Okay. So, one pole from origin come to the minus 4, this pole will come to the minus 4 and this is the angle. So, one will terminate to infinity like this, second will terminate to the infinity like this, and this pole will terminate at the angle of minus 70 and this pole will terminate at the angle of plus 70. So, this would be our final root locus for it. Okay. So, thank you for today. This is the examples of root locus.